All right, so we're finished our models part of this lecture, and I'm just going to wrap up with a little bit of review. So kind of the key takeaways are, what is a model, right? You're taking an abstraction, you reduce a complex problem to its key elements, and then you represent it using some sort of usually mathematical representation or some sort of graphical representation, sometimes both, as we've kind of seen. And then once you do that, you make some definitions on what your solution concept would be. For instance, we're looking at Nash equilibria for all three of these models, the scenario in which there's a mutual best response. And given that there's some solution concept, you can then proceed to solve it using the logic. So a model is basically, in a nutshell, a mathematical or graphical way of representing a complex problem with a defined solution. And it can be conditional. It can be conditional on the relative values of x, y, z, or whatever, whatever variables you're using in that model. But given a certain condition, you should have a defined answer, and a predictable answer, and it should be repeatable no matter who the economist doing it is. And of course, you can make tweaks on your models. You can build more complex models. You can change the assumptions. That's all fine and dandy. And we've seen that. We've seen a change the assumption for the size of D relative to the size of the resource with the Hawk and Dove model, and that changed their outcome. I changed the relative values of X, Y, and Z in the job signaling model in the previous slide. And we got different results depending on that, but the overall model kind of gave us a framework for how to think about a complex economic problem, and it gave us something predictable. And then, if we were testing these models against real world data, if it was available, what we could do is we could look at like the cost of a master's degree and the salary for people who tend to get master's degrees and people who don't. And we could see, does that model accurately reflect the real world? That would be the next step, but we're not going to take in this course, again, because that requires statistics. But the idea is that we build something simple and relatively easy to follow. And maybe your first time seeing these models, it's not so simple. But, probably a lot simpler than it is to become an expert in recruiting and salary and all that kind of stuff, or an expert in price wars and all that. It's not unheard of for people to see this model, understand it in an hour, right? Versus becoming a subject matter expert, which is pretty complex and time consuming. It's a very simple way of doing it. And it's concrete in the sense of we were able to put conditions that determine the outcome. Whereas in the real world, describing things with only using your words, the conditions are there, but they're not really concrete. It's a little more difficult to do without the math. So some of the concepts we touched along the way are abstraction, logic, mathematical modeling, graphical modeling. I talked about game theory a little bit, economic imperialism in the sense that only one of these three models was really about businesses, but they're all kind of microeconomic models. And I guess hiring decisions is more what you expect about it probably falls more in line with your preconceived notions about what economists are doing, but it is a little more than that, because the signaling model can be applied to biology too, right? It could be about how, male gorillas will engage in a fight in order to prove who the alpha is, right? That's kind of like a costly signal too. If you believe yourself not to be the strongest gorilla, you're not going to challenge that authority. That's a signaling model right there. I'm not a behavioral biologist, so I don't know too much about all that. But signaling does have an effect in biology. I do know that much. So in that sense, there is economic imperialism in the sense of using economic methodologies to describe, not traditional economic topics like international relations, like signaling in biology, that kind of thing. What else? Opportunity cost, the best of the foregone options. The utility you would have gotten from the thing that you didn't do, the best thing that you didn't do specifically, take that away. Utility is a kind of a numerical way or a variable way of ranking different outcomes. So your utility from X is greater than your utility from Y, means that you're going to choose X over Y. Your utility from getting hired versus your utility from not getting hired, in what I'm highlighting here, is lower. So if you're hired with a master's degree and you're a normie versus not getting hired with a master's degree, you'd rather not get hired. You assign some utility to this problem, in this case 0 versus negative 0.5, so that you're able to rank the decisions, so that you're able to say something meaningful about what the normie will do. And that's all really utility is. It's just a method of ranking them. So you're assigning some sort of number so that you can rank. Usually it's done in variables in upper level economics, but for this purpose and for all really the purposes you need, you can solve a model completely using like numerical values the way that we did for this one and the Hawk and Dove one. It's not necessary that you provide the values to the variables, but it probably simplifies things in that you don't have to worry about all the conditions. So utility is important. A utility function, which we didn't actually see in these models, but a utility function, or I guess we did in the sense of utility for being hired with a master's degree is 0.5. The utility for being hired without a master's degree is 1.5. That's still a utility function. It's just a little stranger. Oh, I realized my mouse is not. Sorry, my mouse was on the screen of recording, not the screen of the slideshow itself. I apologize. So I was looking at the utility from being hired as a normie versus the utility of not being hired without your master's degree as a normie. That's what I was circling over before. I apologize. But at any rate, the takeaway is that utility is a way of ranking things. And then you can provide a utility function, which is, for game theory, maybe for not for all game theory, but for the game theoretic models that I presented here, where it's very discrete. You're either in this one or this one or this one or this one, right? Your utility function will be U of higher masters, U of not higher masters, U of higher no masters, U of not higher no masters. That would be your utility function, but it's not really a function in the way that you're probably used to seeing it, where you have some good, the utility of eating hot dogs. Where'd that go? Sorry, one second. So the utility of, I'm sorry, it was hamburgers. The utility of eating hamburgers, where you can like simply graph these, right? So utility is an important thing. So if we were to graph these, it would look like, I wish I could just draw directly on here. And I'm not going to draw it, but we had drawn it earlier. So the utility of eating a hot dog for me would look sloping upwards like this. The utility of eating a hot dog for John would be sloping downwards like this, where utility is on the y-axis and the number of hot dogs number of hamburgers is on the x-axis. The utility for Katie was like 2 if it's greater than or equal to less than or equal to 1, and then at 1 it would drop to 0. So utility is just a function we use to, a utility function is the function we use to map a certain number of consumption goods to a certain utility, a certain level of happiness, essentially. And that, again, it's helpful for ranking. So, outside of the context of these models, a lot of times you're going to want to maximize the number of hot dogs you eat, or sorry, I keep saying hot dogs, the number of hamburgers you eat relative to some budget constraint. So if a hamburger costs $2, right? Hamburger costs $2 flat, and my utility of $2 is equal to 4. So U of $2 equals 4, right? I want to know how many hamburgers I would consume. I would consume 4 hamburgers, okay, if a hamburger costs $2, okay, because my utility, I would consume 0.5 hamburgers, because that's the utility I get from consuming 0.5 is 4, which is equal to the utility I get from $2. U of 0.5 hamburgers. Okay. So if I had like a budget problem where I had $2 to spend on, let's say I had $4 to spend on hamburgers, and I could give them to me or to Katie, and I want to maximize utility for both me and Katie, I might give $2 to me, $2 to Katie, or something like that. The utility function will be useful in that sense. I'm not going to, sorry, I had a cheesesteak for lunch, and it's not left me yet. Sorry, that was probably crude too. At any rate, you can use your utility function to kind of help with your budget maximization, getting the most happiness for a particular budget. And we'll see that later on in the course. But the takeaway is that a utility function maps a certain number of consumption goods to a certain level of happiness that you get for it. And that utility functions are subjective. My utility function, John's utility function, and Katie's utility function can all be separate. They're not all going to be the same thing. They're all not going to be 2 hamburgers plus 3, 2 times the number of hamburgers plus 3. And to some extent, utility functions are arbitrary. As long as you still have the same ranking, the same utility function is more or less applicable. Or different utility functions are more or less applicable. The ranking is what really matters. The final thing I want to say is that, for utility functions, is that they tend to actually be sloped in a convex fashion, which is, if we're following the mouse, like this, where the more I consume, the less additional happiness I get. So we'll call this guy Dimitri. The reason I'm picking Dimitri is because Dimitri sounds like diminishing. So Dimitri has diminishing marginal utility. What do I mean by that? The first hot dog might give him 4 utility. The next hot dog will give him 5 utility. The next hot dog will give him 5.5 utility. The next hot dog will give him 5.75 utility. And then let's say 5.8, 5.8005, 5.80005. So each additional hot dog, this is less. 5.80, I want 800,505. So each additional hot dog is increasing his utility for sure, and he would still be willing to pay a certain amount for the next hot dog, but it's increasing his utility by less. Right? The change in utility from going from 0 hot dogs, from 0 hot dogs to 0.5 hot dogs is 4. From 0.5 to 1 is 1. From 1.5 to 5, from 1 to 1.5 is 0.5. From 1.5 to 2 is 0.25, 0.05, 0.0005, 0.0005, 0.005. So each hot dog, he's getting some benefit, but the next hot dog's only giving him a little bit more benefit, and then the next hot dog is even giving him a little less of a little more benefit. So he likes each hot dog. He'd rather consume the hot dog than not, but he's probably not willing to pay a whole lot of money to get from this hot dog to this hot dog, right? From the third hot dog to the 3.5th hot dog. And I keep saying hot dogs, it's hamburgers. I apologize. Okay, so he's got diminishing marginal utility, we'll call that, and we'll define that more in depth as we go on. But so I've plotted Dimitri's marginal utility, Dimitri's utility as the number of hot dogs increases. So basically, as he consumes more and more hot dogs, he's still happier and happier, but the amount by which he increases happiness, the amount of his utility change, is decreasing. So the change in utility is going down, even if the total utility is going up. And you can see that the difference here versus the difference here versus the difference here versus the difference here, which is very slight, and the difference here, which is you can't even see it in the graph. Okay, that's the concept of diminishing marginal utility, and we'll talk about that in future lectures. But this is like the utility function, and if we connected it with a line, it would be like a true utility function. Right now, it's just like a scatter plot. Okay, so utility functions are important. Opportunity cost is important. Your willingness to pay, which maps your utility to a certain dollar amount. So if I'm willing to pay $4 for a hot dog, the utility of that hot dog is the same as my utility for $4. Okay, and I'll use willingness to pay as a stand-in for utility sometimes because it's easier to just rank things in dollars sometimes than it is to refer to some arbitrary ranking utility. Okay. All right, so on to the actual comprehension questions. So key thing that I want you to take away from this class, this is one of the biggest things I think that I'll ask you a lot about and that I think is really important. And it's important not just for economics, but for life. It's because opportunity cost is a thing you'll see. I saw it in a fitness vlog the other day, like, why is opportunity cost being considered in a fitness blog? Because it's important. So anyway, what is opportunity cost? Is it A, the best option, B, how much it costs to embark an endeavor, C, the cost of foregoing something to do something else, or D, the utility you would have gotten from the best foregone option? So is it A, the best option? No, right? Just definitionally, it's not. It's not. First of all, opportunity cost is related to utility, and the best option is more of an action, right? The best option would be like choosing Hawk, not the utility you get from choosing Hawk. B, is it how much it costs to embark in an endeavor? No, that's more about the explicit cost, right? So if it costs $500 to build a casino, obviously that's a bad example, but let's say it costs $500,000 to build the casino, probably still low. But that's your explicit cost, not the opportunity cost. The opportunity cost would be the cost of, or the utility you would have gotten from whatever you didn't do with the land that you built the casino on. Okay? C, is it the cost of foregoing something to do something else? Kind of close, but no. The cost of foregoing something to do something else is more about the explicit cost of the thing that you didn't do. So if you built a casino on your property, but you didn't build a hotel on that property, C is kind of saying more, it's the cost of building a hotel, which isn't true. The opportunity cost would be the utility of that hotel. So that's kind of D. The utility you'd have gotten from the best foregone option. So assuming that building a hotel is the next thing, the next best thing that you would have done if you didn't build the casino, then the utility you would have gotten from the hotel is your opportunity cost. Okay, so it's not just the explicit cost of building that hotel; it's the total utility you would have gotten if you didn't build the hotel. What would the utility you would have gotten from that? The the opportunity cost is the utility from the best of the foregone options. D. I want you to just be thinking about that when you sleep. The opportunity cost is the utility from the best of the foregone options. The opportunity cost is the utility from the best of the foregone options. The opportunity cost is the utility from the best of the foregone options. All right. In the model of the hawk and the dove with mutually assured destruction, Stankonia's utility for being a dove when Rickety Row is also a dove is, so I'm giving you the payout structure here. Okay, so this is Stankonia, this is Rickety Row. If Stankonia is a dove and Rickety Row is a dove, what is Stankonia's utility? It's given right here, 5. Okay, so the actions are dove and dove. The agents are Stankonia and Rickety Row, and Stankonia's utility is 5 when they're both doves. Okay, Stankonia's payoff is on the left, Rickety Row's payoff is on the right, so it's D, 5. Okay, so in the model of the hawk and dove with mutually assured destruction, Stankonia's opportunity cost for being a dove when Rickety Row is also a dove is what? So we know that Rickety Row is being a dove. So Stankonia has 2 options. It can either be a hawk or a dove, right? If it's a dove, this is its utility. But what's its utility if it's not? What's the best foregone utility for when Stankonia is being a dove? Stankonia, by virtue of being a dove, is foregoing being a hawk, and the utility associated with hawk-dove is 10, so B. So once again, when Stankonia is being a dove, the thing that it's not doing is being a hawk. Okay, and the best thing that it's not doing is being a hawk because there's nothing else besides what you're doing and the other option. Okay, so it's not like there's a third choice here and hawk is better. But if there were, you'd have to rank the 2 utilities for hawk and the third choice and see which one is better, and that would be the opportunity cost, the best utility between hawk and the third option. But since there's only one other option, it has to be the utility from the thing that you're not doing, which is hawk. Okay, so 10. All right, so that concludes the lecture. If you have any questions, let me know. I'm going to be posting the journal concurrent with this lecture. So the journal is going to look at, I kind of talked about it earlier, but the model of the prisoner's dilemma in a particular context of this game show. And you're going to have to determine, is the model realistic? What are the abstractions? Where do the abstractions kind of fail? And I think the key bit is communication and kind of mutual rationality, right? Essentially, it breaks down because the other player, I think his name is David, doesn't think that Ibrahim is being rational. He thinks that Ibrahim is acting completely bonkers. And you'll see it when you see the video, but it's a cool thing to think about, and I would urge you to do this particular journal. It can't hurt. If you have any questions about the overall course material, let me know. I think I went on a little long for this lecture. I apologize, but I do think all this information is kind of cool and important. Sorry, not sorry. If you want to listen on 1.5 speed, it's probably late because it's the end of the lecture, but feel free to do so as it kind of goes over. I think that's it. If you have any questions, let me know. Yeah. Have a good week, everybody. Good night.